Okay, we now begin Magnetism, chapter 27. Okay, first of all, the magnetic force. Immediately pause this film and take a look at the first of my demonstration videos involving the magnetic force, showing the similarities and the differences between the magnetic force and the electric force. Okay, now as I mentioned in that film, there are two sides to every magnet. They are referred to as poles. They are called north and south poles for reasons which I will be made clear as I continue. Two sides or poles to each magnet. Okay, like poles repel, opposite poles attract. The reason why they are in fact called magnetic poles is because a magnet will react, if you will, in the presence of a magnetic field that is caused by the Earth. So at this point, pause this film and then go ahead and take a look at my short compass demonstration video. Okay, now that you have done so, basically here's what was happening in that situation, in that demonstration. Okay, here's the Earth, like so. Here's equator, North Pole, and South Pole. The Earth has a magnetic field associated with it that is shaped like a dipole, much like that of a bar magnet's magnetic field. So you may want to pause the lecture again here at this point and take a look at the short demonstration video that I have shown you, or that I have posted for you rather, that shows the shape of a dipole magnetic field. Suffice it to say, however, the Earth's magnetic field is that of a dipole shape, and it looks like this. And incidentally, when I draw the field lines here for the magnetic field, I'm obeying the same rules of field lines that you've seen me do already with respect to an electric field and a gravitational field. Okay, the magnetic poles of the Earth, here and here, are offset a little bit from the geographic poles, the geographical North Pole and the geographical South Pole. And then I take my compass needle, which is just an ordinary bar magnet, and I place it in the presence of the Earth's magnetic field. Let's say, for example, right here. Okay, now one side of the magnet pointed towards geographic north. By definition, and therefore, we refer to this as a north magnetic pole on the bar magnet. And then the other portion of the bar magnet here pointed towards geographic south in the Earth. Therefore, we refer to this as a south magnetic pole. So we define the word pole here to describe the two sides of a magnet in the context of a compass needle that is placed in the presence of the Earth's magnetic field. By definition, the north pole of a bar magnet points towards the geographic north. The south pole of a bar magnet points towards geographic south. Okay, now let's take a look at the bar magnet itself in more detail, and as I said, it also has a dipole shape associated with it. Its magnetic field, that is. Okay, so here is that bar magnet like so. Here's north and south. And then when I showed you in my short demonstration video of the dipole itself, it basically looks, once again, like this. Okay, and then towards the pole of the bar magnet, this is where the field lines are concentrated the most. Therefore, the magnitude of the magnetic field at those locations is large. Whereas off to the side, the magnetic field lines are a little bit further apart from each other. Therefore, the magnetic field off to the side is rather weak. We use the variable capital B to describe the magnetic field, the magnitude of which is just referred to as B. The metric SI units associated with the B field, as we say, is called the Tesla. Which is abbreviated capital T. And one of the mathematical examples that I'll do a little bit later on in the lecture, I'll give you an idea as to exactly what is meant by 1 Tesla. Okay, now by definition, the magnetic field lines point in the following direction, from north to south. So then therefore on this diagram like so, the magnetic field lines look like this. If you want to draw them towards the south magnetic pole over here on the other side of the diagram, that's perfectly fine as well. Now in my demonstration video showing the magnetic force with my torsion pendulum, I mentioned that you cannot isolate the sides of a magnet. You cannot isolate the poles. In other words, when you do have a magnet, there's always a north pole and a south pole. You can't have a north pole all by itself. You can't have a south pole all by itself. Whereas you can, for example, with electric charge, have a positive charge all by itself and a negative charge all by itself. Not so with a magnet. We can describe this mathematically as a flux integral. This is basically Gauss's law for magnetism. Gauss's law for magnetism is the second of 4 fundamental relationships that describe the electromagnetic force, Maxwell's equations. Second. Of Maxwell's equations. Okay, here's then how we describe this expression. What I'm going to do is set up a closed Gaussian surface that encloses both poles of the magnet. It doesn't matter, by the way, what the shape of the Gaussian surface is. I'm not going to do any sort of calculation associated with it. So let's say that right here is a Gaussian surface in black that surrounds the entire magnet. Okay, and then the closed flux integral would be the following. Integral of B dot dA. And then on the right-hand side of the expression, when talking about Gauss's law for electric fields, remember that the right-hand side of the expression in the numerator was the charge enclosed. However, in this case, notice that the amount of flux, if you will, that's going out of the Gaussian surface here at the top of the diagram is the same as the amount of flux that's going in on the bottom of the diagram. Therefore, for magnetism, the right-hand side of the expression is equal to 0. In other words, there is no such thing as a magnetic pole all by itself. Whenever you have a magnet, you always have 2 poles. Therefore, the flux integral for an entire magnet is always equal to 0. This equation has a name. It's called the no-name equation. The reason why it's called the no-name equation is because as of yet, nobody has ever discovered a single magnetic pole all by itself. What is referred to as a magnetic monopole. There is no such discovery of a magnetic monopole. In other words, a magnetic pole all by itself. There are some theories within string theory and inflationary theory with respect to the Big Bang that do suggest that it might be theoretically possible for there to be magnetic monopoles. However, they would be very widely separated from each other in space and time, and as of yet, we have never discovered one. However, if somebody does confirm the existence of one, a magnetic monopole, and then therefore could mathematically describe it, then the right-hand side of the equation would no longer be equal to 0. It's then at that point that the equation itself would be given a name. Perhaps it will be one of you that eventually discovers a magnetic monopole. But as of now, magnetic monopoles, even though theoretically they might exist, as of now, we've never discovered one. Okay, let me do some erasing here. Okay, next, take a look at 2 more demonstration videos. Forces, a magnetic force that is, exerted upon a current carrying wire. And then secondly, magnetic forces exerted upon moving electrical charges. Take a look at those 2 demonstration videos now. Okay, now that you've seen those 2 demonstration videos, what you were seeing in each of those demonstration videos was a specific cross product. Okay, first of all, the magnetic force exerted upon a current carrying wire. The cross product that was described in that demonstration, stated without proof, is as follows. Okay, here are the individual vectors that you saw in that demonstration. First of all, there's a vector that describes the direction of the conventional current, I times L. L is a position vector. L is a position vector basically in the direction of the wire itself, pointing in the direction of the conventional current. So in my demonstration, for example, let's say that the current I was flowing in this direction, and the wire itself has a length L associated with it. The vector I times L points upwards here on my diagram. Okay, and then in my demonstration, let's say that the magnetic field from north to south, from my neodymium magnet, let's say, for example, that that points like so into the board. So right here is the B field, like so. So then therefore the magnetic force that's exerted upon the current carrying wire due to the magnetic field associated with the neodymium magnet is described by the following cross product. IL cross B gives me a force vector in this direction, like so. That was the force of attraction, for example, that you saw in the demonstration video when I was standing like this and holding my magnet like so. Okay, and then what I did in the second demonstration was I basically turned the magnet over. When I turned the magnet over, this then just reverses the direction of the magnetic field. The current, however, was flowing in the same direction. So in the second portion of that demonstration video, I may have gotten it backwards, by the way. Right here is I and L, and then in this case, the magnetic field is pointing straight out at us, like this. And then you saw the following. IL cross B gave us a force vector like so, off in this direction on the diagram, the magnitude of which is described by this cross product. However, a little bit more fundamentally, here's actually what's happening. What's actually happening is that we don't really per se have a force being exerted upon a current carrying wire. Instead, you have a force that's being exerted directly upon moving electric charges. This was the second demonstration that you saw. This involved the cathode ray tube. If you haven't watched that video, go ahead and do so now. So here in this demonstration, you were seeing the magnetic force exerted upon a moving electrical charge. So once again, this is a more fundamental description as to what is going on, because within a current carrying wire, of course, you have electrical charges. Magnetic forces exert forces, or magnets rather, exert forces upon moving electric charges. Not stationary electric charges like I showed in my torsion pendulum demonstration earlier, but a moving electric charge. So for example, let's say that we have a charge Q that is moving in this direction like so with a velocity vector V. And then let's just say I have a magnetic field that is present, for example, like so, B, that's pointing into the board. Okay, the force that's exerted upon the moving electrical charge is described by the following fundamental expression, once again stated without proof. F equals QV cross B. So in this particular diagram right here, Q times V is in this direction, and then I cross like so into the B field into the board. This then gave us a force vector in this direction, like so. That's essentially what you saw in that demonstration as well. So at this point, I'm going to pause. We'll call this part 1 of the opening magnetism lecture. Make sure, once again, that you look at those demonstrations that I just referred to.